Good morning, everyone. My name is Saindeep, and today I'm going to talk about a relatively less researched area of failure management for IoT deployments. Now, we believe that we, uh, we're not paying attention to failure management can lead to significant impediment to scaling up of IoT applications in near future. This is a joint work with my colleagues Palani, Ravi, and Mudhakar from IBM Research. Now, before going into the whys and hows of failure management, let me first explain what we think of when we talk about a smart IoT environment. So, in this case, we have a home environment which is embedded with a bunch of sensors which are going to monitor their environment, or they will going to record information when they are triggered. Uh, Examples of such sensors could be your IoT enabled microwave, which can tell when somebody is cooking, or your IoT enabled toilet flush, which can tell when somebody is actually flushing the toilet. Now, the data from all these sensors is actually going to be recorded via a gateway application, gateway to a smart home application which is running in the cloud. Now, the specific smart home application that we are interested in is remote monitoring for assisted living. Right. So, before I go into the details of remote monitoring, let me tell you what assisted living does. So, assisted living is essentially about helping people who cannot perform some activities of daily living without on their own. So, examples are cooking, washing, eating, and so on and so forth, right? And in this context, remote monitoring for assisted living works as follows. You have a bunch of sensors that you place in the elderly person's home who is unable to perform ADLs or activities of daily living, and you essentially look at the set of sensor signals that are emanating from the home. Now, based on the sensor signals, you try to detect what is the ADL that the person is performing. So, in this case, the ADL could be cooking. Now, this information is going to be looked upon by a medical practitioner who is present at a centralized location, and then on demand send help to the person. So these kind of deployments are expected to be commercially managed and are supposed to scale over thousands of homes and hundreds of devices in each home, right? And obviously, they are expected to provide great convenience to the elderly because they get to stay in their own home, as well as provide efficiency and cost savings to the medical service provider because they can centralize and pool the assistance resources and dispatch them opportunistically. Now, this brings to the problem we are interested in is that devices fail. Now, to understand the scale of failures and how it can be bad, we carried out a simple simulation experiment in which we distributed 10,000 such homes over a 400 square mile area of New York. We placed 14 sensors in each home, and each sensor we assigned a mean time to failure of a year. And we looked at this data for a period of 2 years. Now, from a perspective of resident, what we found is that in at least 50% of the homes, a maintenance visit to fix one or more sensors would be required 12 days or sooner, right? So this is very bad, and very soon the convenience of being able to live in your home becomes a nuisance for the resident. Looking at it from operator's perspective, what we found, or rather what we plotted, is essentially the number of visits that the operator has to do every day. What we found is that in 50% of the days, so at least for a year, the operator would need to visit 750 or more homes in a day to fix the faults that are going to occur. And this is just with 14 sensors in each home. So what makes it more ironic is to realize that given the cheap cost of these IoT sensors, maybe the cost of actually sending a maintenance person would turn out to be greater, right? And this makes the business unprofitable, motivating us to optimize failure management. So with this motivation, let me quickly tell you my problem statement. Our problem statement is that we want to design techniques to minimize the number of operator maintenance visits to these smart homes such that the performance of the application, which is in our case ADL detection, does not fall below a acceptable level, right? So the outline of the talk is going to be as follows. I have already provided a background, motivation, and problem statement. I'm next going to talk about the specific solution that we have built and then talk about results. So let's start by, so before going into how we optimize operator assisted maintenance, let's understand what are the challenges with some simple alternatives to this maintenance done by operators. So one alternative is to add redundancy, which means to begin with put a bunch of sensors in each homes. Now this is operationally hard because these sensors essentially need to be powered, and if you have 100 devices envisioned, most probably you'll run out of power sockets. Furthermore, having a bunch of sensors dangling from your devices, it might be aesthetically unpleasant. The other alternative is, of course, to ask the resident to replace his or her own sensors, which, given the large scale of the deployments, might not work because a significant amount of people wouldn't know what to do. So, given the infeasibility of these other alternatives, let me tell you the key insight, which I'm going to explain later, which we use to minimize operator maintenance visit. The insight is that even though the devices that you have in your home are heterogeneous, you have a microwave, a fridge, a toaster, for the task at hand, which in this case is activity detection, maybe these sensors are functionally redundant, right? So for example, if the task at hand is cooking, maybe a toaster sensor can be sufficient backup for a busted up microwave sensor, and you might not even need to replace it. To leverage this insight, we designed a system called IDEA. Now, IDEA is an integrated system which receives a bunch of sensor events from the home. It does ADL detection using these events. And when sensors fail, it carries out failure management. The first part of which is to detect the sensor failures. The next part is to estimate what is the impact of this failure, right? Is it going to lead to a significant performance drop? And if so, it essentially raises an alert for a maintenance visit. Now, the key technical contribution of this work, which I'm going to describe, is the method we have used to estimate the failure impact, the impact of failure of individual sensors, taking into account the functional redundancy that is provided by other devices in the home, right? Now, before I can explain that, let me first explain how ADL detection itself works in these smart homes. So, ADL detection in the specific use case we have is essentially based on a rule matching method. So, for every ADL that happens in a home, we essentially create a rule set, and this rule set is created in offline manner by mining a set of label data, right? And we use frequent item set mining for this. So here is the example rule for cooking, right? So if you look at it, you have a bunch of sensors which you would generally associate with cooking: microwave, fridge, toaster, water cooler, right? So, and this exactly are the sensors that the rule miner has seen when the person was cooking. And you also have some temporal information, which essentially tells you when this person generally cooks, what is the duration of the cook. So in this case, the person generally cooks between 9 to 10, and it generally takes 30 to 45 minutes. And to match a set of events that you find at the detector, you essentially need to ensure that the rule set is essentially a superset of the events that you're observing. Okay. So obviously, as for cooking, for other ADLs as well, we will have a bunch of rules. And when we receive a set of sensor events, we are going to match the sensor set, which is a match the sensor set for all the rules to determine which rule set is a superset. So in this case, cooking matches, and hence the detector is going to detect cooking. Now let's take another example. In this case, only the fridge and water cooler events were detected. Now, obviously, these two devices are used for cooking as well as for drinking, right? So the sensor set is not enough to distinguish between these two, to discriminate between these two. But fortunately, we also have temporal information. So if you see, the specific event that occurred now is only a 3 to 5 minute event, which is way less than any the 30 to 45 minutes you need to cook. So based on this temporal information which you have mined, the detector is going to detect this activity as drinking, right? And of course, based on the goodness of your rules and how deterministic the person's behavior is, you will have some accuracy of your detector for every ADL, right? So with this understanding, let's try to understand how we can estimate the failure impact, right? So the goal of failure impact is simple. As and when a sensor fails, in this case a microwave failed, we intend to understand what is the impact of this failure on detection of activities, right? So for this purpose, for the detection of this activity, and if the impact is low, you don't need to send a maintenance visit. Okay. So, and to do that, what we do is we need to identify whether enough discriminative rules exist for all ADLs, right? So let's understand what that means. So for example, going back to the previous case, the microwave failed. Now obviously the cooking rule is never going to see a microwave, but if you look at it, any cooking event which still uses a toaster, which is only used for cooking, is good enough, right? As and when you see a toaster, you kind of know that it's going to be a cooking. So the the toaster sensor essentially gives a functional redundancy here for the microwave. And in this case, the impact estimation algorithm is going to look at this feature and say that the impact of loss of this sensor on detecting cooking is 0, no maintenance, right? Now, to make the example a bit complicated, let's say the toaster also fails. Now, in this case, the set of sensors that remain and that are going to trigger when you cook is fridge and water cooler, which is essentially the sensors you have for drinking, right? So obviously the discriminative power of your sensor set is gone. But fortunately, if you look at the time it takes to do cooking and drinking, they're still way different. Now, because of this difference, we can still distinguish between these two activities. So the temporal features also provide some redundancy, right? And in this case also, the impact estimation algorithm is going to accurately detect that maintenance is not required. Now let's look at a case where you actually need maintenance. Assume that the person is going to bathroom and unfortunately the toilet flush broke. Now in this case, when the toilet flush goes away, the rules for going to bathroom and brushing teeth are exactly same. Same sink, same time duration, same time of day. And the system cannot detect that, right? So in this case, the impact estimation algorithm is going to figure out that the discriminative power is gone. There is no functional redundancy present for toilet flush, and then it's going to call up a maintenance. So of course, all of this is possible because we are able to understand how the rule sets are essentially written and what are the different components which help detecting activity. So the system works in other complicated cases also, the details of which are in the paper. Now our system also detects sensor failures and alerts when the impact of a failure is high, but I'm not going to talk about them. The details are in the paper. So quickly looking at some results. So we repeated the first experiment that I have talked about, which is 10,000 homes spread across 400 square miles in New York, 14 sensors in each home. And we look at how many maintenance visits do we need to do in each home. So this is a CDF of maintenance inter-arrival time at each home, right? Now, as we can see from the figure, the nave, which is the traditional system, the inter-maintenance visit time on the average case is 12 days, which we significantly increased to 207 days. So instead of having a person visit every 2 weeks, you have a person visiting once a year. Good. And to look at it from the perspective of an operator, what we have here is the CDF of the number of faults that the operator has to fix daily, right? And as we can see from the plot, this number goes down from 750 in the average case to 68. And all of this is happening because we can significantly delay the various maintenance operations significantly delay the various maintenance operations because we understand what is the impact of the sensor failures by looking at the rules of our activity detector, right? Furthermore, in case of the minimization of visits, our maintenance planning algorithm actually, once it visits a location, also fixes the problems that occur in the vicinity, even if those are not very impactful problems, which further elongates the lifetime of the deployment. So in conclusion, I made the case that failure management would be important for large scale proliferation of IoT deployments, $1 billion, trillion devices and so on. For heterogeneous sensors which are already present in a location, understanding the functional redundancy that they offer to one another is key to provide such maintenance. And we present a novel system called IDEA, which learns these redundancies and estimates the impact of sensor failures. And we show that IDEA reduces maintenance overheads of IoT deployments. So, thanks.